So I have already explained the revised simplex method and tried to calculate a way for the maximization problem. But for the last 2-3 days, I was trying to find out a particular way of solving the applying the revised simplex method in case of a artificial variable when the big M can be used, and how in that case the simplex or revised simplex method can be used. So I have come out of quite a I have done a lot of research regarding that, and seen enough a number of videos, but could not find a suitable video which explains. There are several videos which explains the process, but could not find a particular video in the net where they have explained all the tricks and all that. So I have done myself a lot of problems, and then came out with some process that I'll explain. So if we go back, and I think we have already explained the process of doing the steps of constructing the for a maximization problem with less than equals to constraints, how to do it. So we have already explained that, and we will be taking similar kind of problems. So how we can solve for the viewers, for the students betterment, I have taken 4 problems, and 2 of them are maximization problems, 2 of them are minimization problems with simple first 2 words, or with only less than equal to constraints, and then the next 2 are with equal to, greater than, equals to another constant. So with those 4 problems, I hope I can explain the process of writing the revised simplex table, and hope it will help the students in a very simple manner. So this is the first problem that I have taken. It's a pretty simple problem. It can be solved using graph, and you can always check what is the result and what could be the answer for this. So this is max z equals to minus x1 plus 3x2, subject to x1 plus x2 less than equals to 5, 3x1 plus 2x2 less than equals to 12, and x1 x2 greater than equals to 0. This is a very simple problem. So when we use the slack variable in this case, because the right hand side is greater than equals to 0 and constants are less than equals, so we will be introducing the slack variable and writing the problem in the standard form as max z equals to minus x1 plus 3x2 plus 0s1 plus 0s2, where s1 and s2 are the slack variables, and writing the problem in this particular manner. And to convert that to revised simplex method, we have used the standard form for revised simplex method. So where we write this as write z, so we can transfer this whole quantity to left hand side of the equal to. So this becomes z plus x1 minus 3x2 plus 0s1 plus 0s2 equals to 0, and the other constraints remain as it is. And then generally what we write, and then we can transfer it to the simplex table, where we write this basic variable, then B inverse matrix and other things. Now I have seen the different videos where people are writing z. Actually z cannot be written. Z originally is something. Z is the value that we are trying to find out. So we should not say z is so we are transforming this as a matrix equation. Only the equation we are trying to solve in this case. So and some modifications are done to improve the value of z. So here we are just separating. Here we are separating z. And after z we are separating it with a dotted line, and the coefficients of z are written as this is 1 0 0. So initially then we write the right hand side as this z's coefficient is, so that is denoted by e1, and this particular vector is 0 1 0 and 0 0 1. This, or if you are taking this particular section of the problem, that this is a 2 cross 2 variable, and where the unit matrix is formed by 1 0 and 0 1. So that is, I think, is a better explanation. So this particular part is my important, and where here this is the just the coefficients of with respect to z and the corresponding variables that are there in the basis. So a3 or a4 are the corresponding vectors with respect to s1 and s2, and in the objective function their coefficients are 0. Whether you are taking it this side or that side, it does not matter actually, and the coefficient of z is taken as 1. So 1 0 0, and this part is the matrix similarly is written as 1. So this is 1 0 0 0 1 0 and 0 0. That's how what you have written. But you have if you separate this particular dotted with a dotted line, then as in here z does not have any other coefficient, so we'll be always putting that as 0. And xb is the right hand side. Sometimes in I have seen somebody has written as a b. So this xp is actually the right hand side. Actually this particular value is to be noted here. This particular value is not the value of x. Actually this is the value of z. If you remember, when we write the simplex or bigam table, and in the b column under the, when you calculate zj minus cj, like if we go back, yes, somewhere, yes, see in this particular case, say here we have under the b column, here we have written zj minus cj, and we have calculated zj minus cj for the different vectors. But actually under this b column here, actually the value that we get is the value of z and not the value of zj minus cj. This particular value is of z. So similarly, actually if you think here, in case of revised simplex method, we are just considering the coefficients of the basis vectors along with the value of the z in that particular z row, So yes, the problem that we were doing, as you can see that I have done a lot of problems to come to this particular conclusion, and I'm doing this particular video after this. So, and here it's like yes, a1 a2 are the vectors which are not there in the basis. So a1 is corresponding to x1 and a2 is corresponding to x2. So as in this particular case, in z, this coefficient of a1 is x1 is 1 and x2 is minus 3, and here it's 1 3 and it's 1 2. So this maintains the, then like in simplex. So currently this is the current solution. See, I have tried to write. So current solution, that is s1 is having the value 5 and s2 is having the value 12, and it satisfies the, and by putting those values we get the value of z as 0 also. Now then we calculate the zj minus delta j. Delta j actually is nothing but the zj minus cj value that we talk about. So we calculate, and as we have said, this is a multiplication. This row with this column gives you the value, and for this one this row, for this one this row with this column. So this is negative minus 3. So minus 3 means this is not optimum. So this is the entering vector. The entering vector, actually then we calculate xk, then we calculate how to calculate xk. Xk is similarly, for this particular first value is multiplication of this row with this column, so that gives you minus 3 is this first value. Then the second value is nothing but multiplication of this row with this column, the entering vector column, so this gives you the second value. And third value, this particular value is obtained by multiplication of this particular row with this particular column, so that is 0 into second one, so 0 into minus 3, 1 into 1, 0 into 2 gives you 1, and 0 into minus 3, 0 into 1, and 1 into 2 gives you 2. So these are the three, so that gives you the values of xk. Then we calculate xb by xk, and so for the first one we will not calculate, whatever is for z we will not calculate, that's why the dotted line is put. So 5 by 1 is 5 and 12 by 2 is 6. So minimum ratio is 5 and the vector corresponding to minimum ratio leaves. So S2 leaves and X2 enters. So in the next table we write Z, X2 and S2, and this column will become 0, 1, 0. So accordingly we change and we use the rules that either you can use the row transformation rule and or the formula that we have discussed in case of simplex, that is new element equals to old element minus p into q by pivot. So this is a pivot or key element, and p into q by pivot. So p is the corresponding element of the so when you are calculating this say this particular value, then corresponding element in the pivotal row is this and corresponding element in the pivotal column is this. So this is 0 minus 1 into 2 by 1, so that gives you minus 2. So this way all the elements are calculated over here. So the current solution is x2 equals to 5, s2 equals to 2 and z equals to 15. So if you put those values, you will get z equals to 15, and then you calculate delta z or zj minus cj. So 1 into 1 is 3 into 1, 0 into 3 gives you 4, 1 into minus 3, 1 into minus 3 is minus 3, 3 into 1 is 3, so this gives you 0. So all zj minus delta j's are greater than or equal to 0, then hence the solution is optimum. Hence we get the solution as, so this is a pretty simple problem and this format satisfies. Now what happens if the problem is given as a minimization problem? Then how we can write the standard form, and what kind of form is how you can write for the revised simplex. So here is another problem that we have taken as this is the second problem that we have taken as minimum z equals to x1 minus 3x2 subject to minus x1 minus x2 less than equals to 2, x1 plus 2x2 is less than equals to 2. We have taken only the less than equality constraint for the time being to explain a little bit, then we will take the different kind of constraint. So the general standard form that we write is in the form of max z dashed. So if we write max instead of z, we'll be using z dash, because this z and this z are not same, the values are different. So we'll just changing the signs, we get, so this becomes minus x1 plus 3x2, and here we have introduced the because right hand side was greater than equals to 0, and we have just introduced the slack variables because only slack variables were required, and we have formed the constraint. And see, if you can see that here we have written the revised simplex standard form as, I have not written in terms of z, but instead of that I have written that as z dashed. So z dashed, so because z dash is my max value, so z dashed, I'm shifted this to this to make that, so z dash plus x1 minus 3x2 plus 0s1 and 0s2 equals to 0, 2 and 6, and similarly we have we have written that basic variable b inverse e1, e3 and e4. e1, a3 and a4 are my basis. So here also 1, 0 and 0, 1, and other than z dash that I have, and the coefficients are like, so this is 1, 0, 0, 1, 0, 0, then this is 1 and minus 3 for a1 and a2. a1 is for x1, a2 is for x2. So this is minus 3, and this particular part is the unit matrix, and xb is the right hand side, as we have said, 0. Again, let me emphasize, this value is not this value is the value of z. This value is the value of z. Every step, whenever whatever we are calculating, this particular value gives you the value of z. Every time this value gives you the value of z. In this case, this value gives you, here the value is z dash, not z. In this particular problem, because the original problem was minimization z, so we have changed that to maximization of z dash. So in this case, every time in this, here the value is of z dash. So and so the current solution in this case is s1 is 1, s2 is 2, sorry, not this one, xb, the values in the column. So s1 is 2, s2 is 6, and z dash is 0. If you check, check that, so s1 is 2, s2 is 6, so that is the solution, and but that does not contribute anything to the value of z dash. And then we calculate delta j like 1 into 1. So this gives you 1, and this gives you minus 3. So minus 3 is minimum, so it enters. So this is the entering vector. Then this particular value, this zj minus c, this value actually comes over here in xk. Every time it is like that. Every time this value corresponding to z, that maximum value, z dash means max function's corresponding value will always be this value, or the most negative, that is that particular value that is entering, that will come here every time. So this is 1 into minus 3 plus 0 into 0, 0 into 1 and 0 into 2, that gives you minus c. So this particular value comes here in the xk. Then for second and third values, we calculate this row into this column, so it gives you 1, and for this third value we get this row into this column, which gives you 2. So this is the corresponding xk, which will be used in case of revised simplex, and we have to calculate the exit vector or the variable that is exiting the basis. For that we have to calculate the xb by xk ratio. So 2 by 1 is 2 and 6 by 2 is 3. That gives you, this is the minimum ratio. So that is this arrow will indicate that this is the exiting vector. So s1 goes out and x2 enters. So in the next table we have written the same way. I have put a dotted line under z dash throughout, and instead of s1 it is x2 and then s2. And then we have done the similar kind of calculation, either row transformation to make this as 0, this as 0 as well as this as 0, to do the corresponding changes. Or you can use, as I've said, say if you want to do this particular, so this value becomes 0 minus 3 into 2 by 1, that gives you 6. Or if you use the row transformation, so using this row you want to make this particular value as 0, so just multiply this by 3 and add. So if you multiply this by 3, you will add this, you will get this. So this becomes 0, multiply with 3 and add, this becomes 1. You multiply 3 and add with this, so multiply 3 plus 0 is 3. This remains. So this is how we are. For this, to make this as 0, you multiply with this as 2 and subtract from this row. So this gives this remains 0. So this 1 you multiply it by 2 and subtract from this, so 0 minus 2, so it gives you minus 2. 0, it remains 1. So you multiply this by 2 and subtract from this, so 2 into 2 is 4, 6 minus 4 is 2. So this is how we get. So this current solution gives you that x2 is 2, s2 is 2, and z dash, value of z dash is 6. So and again we'll calculate delta j. If you observe for the previous problem, this a1, a2, these values we have never changed. These values we will always remain unchanged. This from the original problem. So this will be used only for calculating the values of delta j or zj minus cj, whatever you like to call it. So here now what we get is 1 into 1, this 1, 3 into minus 1 is minus 3, and 0. So 1 minus 3 gives you minus 2. This is 1 into minus 3 is minus 3, so 3 into 1 is 3, so this gives you 0. So this minus 2 is most negative, so this enters. Then we calculate. So as I've said, then we calculate xk. So always that entering value of delta j will come at top of xk, at the row of z dash dot z whatever. So this value minus 2, this is 1 into 1, 3 into minus 1, 0 into this value is minus 2. Then for second row, with this you multiply 0 into 1, 1 into minus 1, and 0 into 1, so this gives you minus 1. And this one is 0 into 1, minus 2 into minus 1, that gives you plus 2, and 1 into 1 gives you 3. So this is minus 2, minus 1, and 3. So xk value changes to 3. And then we calculate the ratio or xb by xk. So for z will not calculate. Now for this one, this is minus 1, this is 2, xb is 2, and xk is minus 1. So we will not calculate for this one also, because this value is negative, and only 3, 2 by 3 is, this is 2 by 3. So this goes out, this goes out. And the pivotal, this becomes pivotal row, and so this is the entering vector, this is the leaving vector. So pivotal row and pivotal column, so we have to divide by pivot. So 3 is the key element of pivot, so we have divided by 3 to get this and all other values. Then in this case the current solution becomes x2 equals to 8 by 3, x1 becomes 2 by 3, and this is 22 by 3, and we all other calculations are done the same way, and again we get delta j, and we get the values as all of them are greater than or equals to 0. That means the solution is, this gives you a optimum solution, and hence the optimum solution in this case becomes x1 equals to 2 by 3, x1 is 2 by 3, x2 is 8 by 3, and max z, mind the z dash is max, so z dash is 22 by 3, so mean z is minus 22 by 3. So that gives you the solution. So we have these are the two simple problems. One is max on the max form, and one is in the mean form. So here much changes are not very much bothered, more or less similar, but to use revised simplex for big M, then it is a little bit of changes are required. So we'll discuss that in a moment.